Hi, my name is Adam Vaughn. I'm going to talk about a continuously variable intake manifold that I designed and built for our Formula SAE race car at the Cooper Union. For those that don't know, Formula SAE is an engineering competition where students design and build from scratch a Formula-style race car. It's held in a number of locations around the world, and the most popular of those locations is in Michigan, which typically sees about 120 teams, and a sizable fraction of those teams are from outside of the US. This particular project was part of my 2010 master's thesis, and if you're looking for a good paper reference for the following slides, I would refer you to SAE paper number 2011-01-0420. So you might ask, well, why would you want a variable intake manifold? Well, the primary benefit is that it's easier to drive, and we'll get into the details later. But basically you'll end up with a flatter torque curve, which means your car will accelerate at more or less a constant rate. You won't have as many operating points or speeds where the engine wants to accelerate more or less than others. You'll also have this constant torque over a wider range of engine speeds, which means that you can shift less. As for why you would want this over, say, a turbo, is just the sheer fact that most of the cars at this competition don't finish. The primary failure mode for a variable intake is a static intake that doesn't vary, and the engine can still function in that case, versus, say, a turbo where the main bearing fails and you have a giant plume of smoke, which would easily disqualify you. Another benefit of this project is that it's great for developing 1D models because you can actually try out different configurations in the intake manifold fairly easily. Formula SAE as a competition has a number of rules that are designed for both safety and ensuring that the same class of car shows up from all the different schools. For the intake manifold, one of the primary constraints is a 20 millimeter flow restriction. This limits the amount of air that can get into the engine, which limits the amount of fuel that can be burned with that air, and in turn limits the maximum amount of power that can be achieved with the engine. Another constraint is the packaging envelope, which we'll get into later, but basically it limits the amount of space that is available for fitting the intake manifold on the car. Other constraints include the maximum size of the engine cannot have a displacement greater than 0.61 liters. One of the primary design variables of an intake manifold is the length of the tube that connects the back of the intake valve to the plenum. I've shown this schematically in the upper left by the green line, but note that the green line does not include the length up to the valve. To see this extra length, please refer to the lower right drawing that includes a rubber mold that I made of the intake port geometry that's inside the engine head. This head geometry I can't change because it's part of the engine, but it is worth noting that it does impact the placement of all the other components around it in terms of packaging, such as the fuel injector. The primary contribution of my work is a new way to continuously vary this runner length in such a way that it also achieves a large range of variation, much larger range than you could achieve with a tube inside of a tube design, and it also has a smooth flow path into the cylinder. To help visualize this half-tube sliding mechanism, here is a short video that shows the final fabricated intake manifold being actuated by hand. Because the runners are being slid by hand, the motion will be not as smooth as with a servo motor. The overall layout of the intake manifold is impacted by a number of considerations. One of the most significant of which is the surface envelope shown in the upper right. No component of the intake manifold may be placed outside of the red dashed line. Other considerations include the distribution of air between the cylinders, wherein it's desirable to have the air enter from the top versus the side, because side entry is prone to having unequal distribution between the cylinders. Even with top entry, there are still differences between the inner and the outer cylinders. Other considerations include the overall length of the restrictor, where I've done simulations and seen that a long restrictor is desirable, and such things as the orientation of the fuel injector, such that it is pointed directly at the back of the intake valve. To design my intake manifold, I first began with basic Helmholtz equation calculations, and then I moved on to 1D CFD simulation with the Ricardo Wave software package. This software allows you to draw the layout of your engine in terms of one-dimensional flow elements, which can be seen as the black lines in the diagram at the top. The primary benefit of 1D simulation over, say, 3D simulation is that it executes very quickly. However, it does not capture turbulent effects nearly as well. In the lower left, you can see a design of experiments that I performed varying the runner length against engine speed. You can see that there is a ridge of peak torque that moves as a function of engine speed. If you were able to vary the runner length as a function of engine speed, you could maintain this peak torque for a larger range of engine speeds. Because 1D simulation does not capture turbulence effects well, I designed some software to perform a design of experiments with the ANSYS Fluent software package so that I could run simulations of the restrictor, where turbulence is an important factor. From this, I arrived at the final geometry, which you can see in the top diagram. I also performed 3D steady-state simulation of the overall intake manifold geometry. It is worth noting that the 3D transient simulation is really what's needed here. However, my project did not have enough time to run a full 3D simulation. Each of these steady-state simulations, as a point of reference, takes about a day to run. And I went through many iterations to try to resolve the general issue of recirculation, which I saw on the left, and also deciding between different intake runner trumpet geometries, which you can see in the lower right. Finally, after many design iterations for both packaging considerations and also flow considerations using CFD, the intake manifold was finalized and fabricated using both CNC and 3D printed molds. The material that is mostly made out of is carbon fiber, which was done using a wet layup process and vacuum bagging techniques. And you can see the final product installed on our dyno engine on the left, and with the cover off on the right. Although I do not have enough time in this short video to go into full detail, there is a whole other side of this project that deals with the electronics of asking the engine control unit what the current engine speed is, and then commanding a servo motor to move the intake to the optimal runner length. This is done using a DS-PIC microcontroller that communicates with our MicroSquirt Engine Control Unit over something called Controller Area Network, or CAN. In the figure you can see the request packet followed by the reply packet from the Engine Control Unit. This particular oscilloscope has the ability to decode CAN packets, and the hexadecimal numbers along the bottom show what those packets contain. Here you can see actual engine results at wide open throttle. These were done with a preliminary engine calibration that used closed-loop lambda control to adjust the fueling based off of the air-fuel ratio and exhaust. This is necessary because each of the runner lengths flows a different amount of air. It also used unoptimized stock cams, which are not great for restricted engine configurations. So between those things, I think there's more room to grow. But that being said, on the left you can see the maximum and minimum torque envelope for all different runner lengths tried between the shortest and longest runner length, along with 289 millimeters highlighted as what I felt would be a good non-varying runner length from those data. On the right you can see what this all means in terms of engine power, and between both of these plots you can see how varying the runner length affects what your engine characteristic is. Here you can see the original Ricardo Wave simulation results on the left and the preliminary engine results on the right. You can see that there are differences between these two plots, and it's clear that more work needs to go into the simulation to match the experiment, which I might add that the simulation was done before there were experiments, so there is some fine-tuning that needs to happen. But that being said, there is a clear ridge that you can follow on the right to maintain high torque as you go to higher engine speeds, which is the expected behavior. Here you can see the transient response of the intake manifold on the left. The red curve is the torque measured, and the green curve is the servo-commanded position of the intake manifold. These data were taken a couple months after the original data set, but I'm including the original data set on the right so you can see conceptually what's happening. We are starting from a long runner length, and we're going up over the ridge following the dashed line on the right towards a shorter runner length. So we're going up and over the hump, and you can see that's reflected in the results on the left. So in summary, this video shows the design, the analysis, and actual testing of a new continuously variable intake mechanism. The design actually achieves greater than 22% more power than the previous unoptimized static intake, and it can vary the engine's resonance peak in real time as the engine is running. As a result of this, you wind up with a more drivable engine because you can maintain the peak torque for a larger range of engine speeds, and you're not adding much in terms of weight to the actual engine with this mechanism. It was only briefly discussed, but there is a CAN microcontroller network that is actuating the intake based off of the measured engine speed. There was also a platform developed to run automated Fluent studies for the restrictor optimization. And although it wasn't discussed in this video, there was also some FEA work that was done for the carbon fiber. In terms of future work, one of the main things is optimizing the intake cam profile for the low pressures in the intake manifold caused by the restrictor. There also should be some additional dyno testing, but one of the main issues that I encountered was testing and cooling issues need to be fixed. Being able to measure volumetric efficiency directly would be really beneficial because that decouples the performance of the intake from how well the combustion is going in the cylinder. Refining the engine calibration, looking at part load, and looking at fuel economy, the BSFC. Also expanding the CFD simulations, calibrating the Ricardo wave model would be really great to capture those differences that we saw between the experimental and measured. 3D simulations, and also throwing in the actual design-based optimization. More FEA simulations would also be great, and even more importantly, actual track data would be absolutely awesome to get.